Hello, my name's Jamie Justin and I'm the founder of Dotted Eyes. I'm going to talk to you today about cartographic rendering tricks for OS VectorMap Local using FME. So a few words first about this project. OS VectorMap Local is a vector dataset for which the first version was released by Ordnance Survey in Great Britain in September 2009. It needed really quite sophisticated processing to render it properly. Ideal really for a partner with technical skills like ourselves. That was followed shortly afterwards by version 1.1 in April 2011. And Ordnance Survey changed the data structure significantly then to make it much easier to load and more suitable for end users. So this talk is going to be about version 1.1 and subsequent releases. Ordnance Survey emphasises with this product the flexibility that can be applied to vector styles. Of course that's true really of any vector dataset, but particularly relevant in the context of OS VectorMap Local. And today's goal is to implement those styles, particularly for GIS and CAD users. And really our goal is to process the data centrally and then render it anywhere in any kind of client software. And it raises the question, how well can FME do cartography in addition to its extract, transform and load, or ETL functions? And can its universal viewer actually give you a reasonable preview of the finished look, even though it's not itself a real GIS system and never will be? Looking at Ordnance Survey's website, there's a whole page on OS VectorMap Local which describes the product, and I've ringed in red here a link which allows you to download the user guide and technical specification as a PDF document. And if we open that up, here it is, the front cover of the PDF document, and inside it, the first view we get of the data set is on page 6 here, where it's just an unstyled rendering of the raw data. And there are a few notable characteristics. If you look just above that box with red text in, you may see some road names, and there are actually two sets of cartographic road names on top of each other, as it were, intended for use at different scales. In addition, each road has a centre line running through the middle of it, as well as casing lines either side. There's a big urban area for the whole built-up region, which can obscure other features depending on which order you draw them in. And there are also contour lines and labels that may need special treatment. Now here is a view actually taken from MapInfo Professional, but of Ordnance Survey's 1 to 10,000 scale colour raster product. So this is already rendered in the form of an image, and really our objective for today is to approximate this appearance using the vector dataset OS VectorMap Local. After we've done that, we'll consider what's involved in making changes to the rendering style. If you look back to the PDF document, which is the user guide for the dataset, Chapter 4, as I've ringed in red, consists of style specification tables. And here's one of them, the 1 to 10,000 scale raster style, which corresponds to the view we've just seen. I've taken that same information and just copied it out of the PDF table and pasted it into an Excel spreadsheet. Actually, if you've ever tried to copy the contents of a PDF table like this, you'll know it's quite tricky, but we've done that and put it in the spreadsheet, which I shall be using today, and we're going to make available free of charge on our website for you to download if you're interested. There's one column which I've renamed to table name. It was formerly called member type, and we're going to use this to show how the spreadsheet can be a sort of control panel to organize how FME actually operates. So you can simply type new values into that column. But first we'll use a filter to show the values that are there already. And this collection of values corresponds exactly to what was in the PDF guide. But now, by editing the values in certain cells in there and rerunning that filter, you can see I've got additional output layers. So I've typed in, for example, polygon landform to a few cells, and we're going to use that in an output table which will provide hachering. That's the indication of slopes and cliffs. We're going to also separate out line contour and text contour so that we can control the drawing order of those. Now a little look at colours. If you're accustomed to working on the internet, you may well recognise these RGB values of colours, which are not quite the same ones that FME expects. It wants little triplets of values between 0 and 1. And there are various options for getting from the RGB to FME colours. First option, you could use lots of FME transformers to do it. And of course you could combine those up into a custom transformer for simplicity if you wanted. Or option 2, within a single transformer you could use a tickle procedure, but I'm not really a programmer, I'm much more of a data guy, so that doesn't tickle my fancy. But since we've got Excel here, why not just add new Excel columns and put formulae in there that will get the values we need? So that's the option we're going to take today. And I've now added 2 new columns to Excel, one called FME Color and one called FME Fill Color for the inside of region areas. And this is the formula that you need to put in a particular cell to do the conversion. Just to have a quick look at it, the part in bright blue in the middle says find the place in the cell that contains a hash value, and then we're going to look at pairs of RGB values coming after that, the red pair, the green pair, and the blue pair. The reason you need to start by finding the hash value, can you see just underneath the box which has got that formula in it? There's one cell which has a value in brackets. Ordnance Survey supplied it like that in the PDF, and we've carried that through into the Excel spreadsheet. So you can't assume that the hash sign comes right at the start of the cell. After we've found it, we'll take pairs of values, we'll convert them from hexadecimal to decimal, and then divide the result by 255 to get a value between 0 and 1. We'll round it off to 3 decimal places and concatenate together the 3 values with commas in between them. And then there's just a bit at the very start of this formula which says if the cell we're starting from is blank, we'll make our result blank as well, otherwise we'll fill it with the value. So that's exactly the formula you need, which you can then copy and paste all the way down a column to work out the FME colours. And looking at the bottom, you'll see I've got a number of tabs in this Excel workbook, one for each of the styles that's in the Ordnance Survey PDF style guide. There are 6 of them altogether. And I said we're going to make this available for distribution. It comes with the metadata shown here, which acknowledges the Ordnance Survey Crown copyright in this original material, and also just points out that there are 1 or 2 corrections we've made in this spreadsheet. It actually boils down to deleting a duplicated row and also sorting out a few values which have plainly been put into the wrong columns. But other than that, it's exactly the same as Ordnance Survey Publish, and we're making it available free for you. So now this is an exercise using FME. Let's start up the FME program and choose the Generate Workspace option. And that will produce this dialog box where we can pick OS VectorMap Local as the reader we want to use and MapInfo tab as the writer. And by default, it uses the static schema to get between the reader and the writer. So if we run that, it's going to parse all the GML content of the input file and find which data types are in the GML data. And here's a list of them. We'll leave them all ticked as they are by default, so that when we run to the next stage, that static schema choice results in a separate reader for each data type connected to a corresponding writer for that data type. This really isn't the way we want to use the FME software for this exercise, because we want to control it through the Excel spreadsheet. So instead, going back to the beginning, let's choose the alternative option of dynamic schema, which allows us to fan out to various different output tables based on one FME writer. I'll show you what I mean. When we choose this option, it provides just one reader for all the data types inside the GML connected to one writer. And if we double-click on the reader or use the ellipsis, the little button with 3 dots on it, it says that the wildcard star applies to the reader, meaning that all the feature types will come together through that input source. And double-clicking on the writer gives us, by default, the bottom part of the dialog box, dynamic properties. We're actually going to change that later, but I'll show you first how it looks that way. And now in order to use the spreadsheet to control the output, we have to join the values in the spreadsheet to each of the features that come out of the writer. To do that, we use a joiner transformer, which consists of a wizard. So we tell it to open the Excel spreadsheet, and you'll see there the 6 tabs that were along the bottom. We'll pick the 1 to 10,000 raster style. Say that the unique key in our data is the feature code, and that's also the name of the foreign key we're going to use to join it to. And then all the other attributes from the spreadsheet will be picked up and attached to each feature. Then I'll just click through by default the other steps in the wizard, and now I'll go back to the writer and double click it again, and you see I've cleared the checkbox near the bottom of this that says dynamic properties, which activates the part at the top that says fan out by attribute, and we can now pick up the column table name from the spreadsheet and use that to define the name of the table that each feature will go to. I'll also specify the user attributes that I want to pick up, and the ones that start with a small letter, feature code, feature description, and at the bottom GML ID, have all come from the GML data, but the ones that start with a capital letter are columns out of the Excel spreadsheet that are being joined to the features. So now if we click the Run button in the FME workbench, we'll get some output tables. And I'm viewing them here inside MapInfo Professional for convenience, but you'll see on the left-hand side in the layer control the names of the tables which have been taken from the Excel spreadsheet. And in the main map window, you'll see a view that looks very much like the map that was shown in blue on page 6 of the Ordnance Survey PDF guide. In other words, all the information's come through to the output writer. And if I click on one of the lines, this particular one has attributes that show it's a parish or community boundary and define the line style that Ordnance Survey suggests we should use, a stroke width of 6 meters on the ground, and in the further description it suggests a dashed line of 6 meters long with a 27 meter gap in ground units between the line dashes. Obviously we haven't got that at the moment. All the features have just reverted to a plain, black, simple styling. So now what are we going to do about improving on it? Well, first of all, we want to just fill in FME's default colours. If the spreadsheet doesn't give any values for FME colour or FME fill colour, we'll fill it with the defaults that are shown on the right here. We'll also rename those columns to exactly what FME uses internally to define its colours, which has a North American spelling there, as you can see under New Attribute, and it's all in lowercase. It raises the interesting question, why not just start with those other names inside the spreadsheet? Well, they're sort of reserved words, and if you try and do that, then the joiner transformer will actually ignore any of those reserved words. So this is a kind of cheat or a workaround where we're reading them in one form and then renaming the attributes to a different form. And when we run that, you'll see that we've got some fill colors now applied to the polygons, but the big black area filling the whole of the bottom left-hand part of the map is really the edge of the urban polygon that I talked about earlier, certainly obscuring all the other features except contour lines which are drawn on top of it. And the reason for that is that there's no explicit instruction in the PDF document to omit any features. But it turns out that what you have to do is read the colors and the further description columns, and if all of those are blank, that seems to mean leave out this feature and don't render it in the current style. And omitting features is a vital part of the editing process. So going back to our workbench, we'll put in a test transformer that has a look in the FME color, the FME fill color, and the further description column. And if they're all blank, then we'll simply ignore the feature. Look on that transformer and you'll see that coming out of the tester, if they pass this test, the features go nowhere else. But if they fail the test, then we're sending them down to the map info writer in the bottom right-hand corner, and also out to an FME inspector. And when we do that, certainly that big urban area polygon's been omitted now, and we can see underneath it we're hiding the buildings and streets and all the other information on the map. There are still some black polygons which we want to preserve, but we want to improve their styling, so that'll be our next step. And to do it, we're going to now filter according to the table name attribute. So we're going to start working on specific table names with a little bit of logic for each one, beginning with the polygon member. And here for polygons, we're going to have just a few extra processes. One is if there's a null value in the color attribute, we're going to replace that with the white color. And then, because these are all polygons, we're going to take whatever the fill color is specified as being and apply the same thing to the edge line around the polygon. Let's have a look at that in larger scale. You can see what I've been describing, and then when we run it, we get this result. Something that already, although very pale and just showing the fill colors, already starts to resemble the 1 to 10,000 scale raster we're looking for, in the sense that there's some blue for sea down at the bottom right-hand corner, and some yellow for the sandy beach close to that. You can see a few areas of green, particularly in the top right-hand corner for woodland, and then buildings filled with that very pale terracotta colour. So we've dealt with filling polygons with solid colour, but the next thing we want to do is apply some patterns to them to resemble those in the 1 to 10,000 scale raster data set. And just making this a bit bigger, you'll see that we're taking the polygons here and testing, particularly for whether they're vegetation, that sort of thing, in the string searcher, having a look in the further description column to see what they're described as being. And if they're described as needing a symbol pattern to be applied, then we're sending them to a custom transformer called the area symbolizer, which has been created specially to do this job. Then we'll create an attribute to say, instead of sending these to the same output table, we'll send them to a different output table that can be drawn on top of the solid fill, and finally clean up some of our working attributes. So when we run that, we'll get the right result. But I just want to acknowledge, first of all, that this area symbolizer transformer, which I've written, relies on the symbol filler transformer, which Dimitri at Safe Software had made available through FMEpedia here. And in turn, that incorporates the hatch pattern creator. So you see how you can nest custom transformers inside each other, but adding additional logic and doing specific jobs that are needed for a particular project. Running that, we get the same fill patterns we had before, but now some symbols drawn on top, particularly indicating vegetation towards the top of the map here. And if you look in the bottom right, you may see just south of the sandy beach, there's some shingle indicated by that small pattern scattered through the shore. And so this is an effect very much like the one that's done by Dotted Eye's interpose or superpose software for OS master map topography layer, or indeed by our more recent MISO data optimizer service, which also produces this fill pattern that's using Ordnance Survey symbols. And in addition to that, there is some landform information about cliffs and slopes and that kind of thing. We'll simply take that from the attribute filter on the top left, and we'll have a look at what happens when we send that through. Now you'll see that there's a very sophisticated pattern of rocks in the sea and complicated cliff structure, and even the portal to a railway tunnel in the centre at the bottom of the map, very clearly portrayed. But I've highlighted in the red area that there's also some simple lines. These are meant to indicate earthworks and embankments and that kind of thing. And Ordnance Survey in the PDF document says, in brackets, show if symbol easily created. Well, of course, that's the whole purpose of this exercise, to make things easy to create. And to do it, we've got another custom transformer. Just expanding the view of that shows that it's called the Hashur creator, written for the purpose of creating additional Hashur patterns from those simple lines that are provided in the data. And running that, you'll see the effect inside the red area. Now, instead of simple lines, we've got patterns which very much correspond to those that are already in the data, but indicating precisely where the earthworks are in the far top right-hand corner of the map view here. The next feature type we'll have a look at is points. And if I expand the view of that bookmark, you'll see we're taking the points features in and filtering them according to whether they represent an antiquity site. If they do, we're going to apply some special treatment to them to create what in heraldry is known as a cross-pomme. A cross-pomme actually comes from the medieval French for a cross which has got pommels on the end. And here's a picture of one taken from the 1 to 10,000 scale raster image, indicating in this case a Roman villa. But you see the cross-pomme symbol there. Now it so happens that I'm using the MapInfo Professional cartographic font to represent most of these points, but it doesn't have a cross-pomme symbol. So I've created a cross-pomme custom transformer which draws that specifically. All the other kinds of point features simply go through an expression evaluator to set the correct size and then go into a symbol renderer and come out looking like this. So in the far top right-hand corner is just a little dot indicating the historic feature there. Towards the centre of the map is a triangulation point. There are also several spot heights. And if you look right at the bottom, you'll see highlighted in red is our cross-pomme. So that's how the symbols are going to come out. And the next type of feature we'll look at is text. Now there's a terrific lot that can be done with text, particularly refining its exact position on the map to improve the cartographic appearance. But that goes a bit beyond the scope of this half-an-hour session today. So just looking at what we are going to do with text, first of all, replace any null attributes that don't define the font with something more specific. Then have an expression evaluator which deals with rotation, because here Ordnance Survey defines the rotation in tenths of a degree, so values between 0 and 3,600. And FME expects to see these in degrees as floating point values with decimal points. So the expression evaluator simply divides them by 10. We then look up the font attribute, because the values given by Ordnance Survey for font are a sort of shorthand for the official name, and we need to give the exact name as known by Windows so that FME can find that font, and then put it into a text stroker which will stroke them out and render them actually as polygons, and finally replace null attributes in order to get the right colouring of the text. And the result of running that is to scatter text features around the map, rotated where they need to be, following the orientation of the streets and the roads, for example, and using various different kinds of font. So if we zoom in a bit towards the bottom right, very near our cross pomme, you'll see a Martello Tower, the site of an antiquity, using a Gothic style font for that purpose, and contrasting with the plainer Arial font for every other feature. Moving on then, let's next look at line features in our workbench. Expanding that view, we're going to search through the string in the column further description to have a look for the pattern of dots and dashes that's been specified for each line. So we're going to pick out, as we saw in the earlier example, the value 6 for the length in meters of the dash, and the value 27 that we saw earlier for the value in ground units between dashes. Concatenate those together as a list separated by commas, and send it to a custom transformer called the line pecker, which takes a solid continuous line and turns it into a dashed or dotted line according to the specification. Then we'll take the output from that and send it to a line polygonizer, because the easiest and most effective way to make sure that the width of the line is rendered exactly the way we want it is in fact to turn the line into a polygon. It has about double the number of vertices, but that's not a big issue and doesn't really affect the draw time very much. And then we'll just copy whatever was meant to be the line color and make it the fill color of that polygon, clean up any surplus attributes, and here's the result. So you can see we're adding lines, some of which are dotted and dashed, to the picture we had before. I must say, to my taste, that looks as though it's all a bit heavy now and the lines seem a bit thick. So let's just zoom in one area. And in MapInfo Professional, I've picked up the attributes of that line which is running roughly from north to south, a district or London borough boundary. It's defined as having a stroke width of 5 meters on the ground by Ordnance Survey, and I've used the ruler tool to actually measure it in the map, and it's come out to exactly 5 meters. So it's being rendered according to the specification, but it does look a bit on the heavy side, I feel. That's fine. We've provided a scaling factor in as an attribute that can be used in the custom transformer. So if we enter 0.25 as the value of that scaling factor, it'll reduce the thickness of all the lines here to a quarter of what they were before. And as you can see, the line that was specified as 5 meters is now being rendered at 1.2 meters, and to my eye gives a more pleasing effect to this map. By the way, just while we're zoomed in having a closer look here, you may notice in the green areas are those symbols that were drawn earlier, and they're cropped to the edge of the polygon. You can also notice that there's an electricity transmission line running from the bottom left-hand corner up and to the right in this map view, and there are pylons indicated on the map which are rotated at a specific angle along that electricity transmission line. That's part of what we were doing with the symbol placing transformer earlier. But now going back to our previous view, you can see we've got the polygons placed, we've dealt with the symbols and the landform areas, and now we've added text and also lines. But it's not quite finished yet, because the raster data has grid lines at 1 kilometre intervals. Well, now the GML data contains no features corresponding to those grid lines at all, but there's a bookmark here that creates the grid from scratch. Notice there are no lines coming in from the GML reader to this bookmark at all, simply a line going out to the MapInfo tab writer. That's because there are no features supplied corresponding to the grid lines. But what we're doing is creating a null feature, a feature with null geometry, then fetching as a parameter the name of the GML file, which I think in this case is something like TR35NW. And we're breaking down that name to work out exactly where on the national grid it sits, and drawing 1 kilometre grid squares for 25 separate squares within the 5 kilometre tile that we're reading, and writing those out to a new MapInfo table called grid square. So when we do that, this is just a reminder, this view, first of all a reminder of exactly how the raster image looks in MapInfo Professional that we're trying to emulate by styling our vector data. Now for the same area, I've switched over to the actual rendering of vector, and I hope you'll agree that all the features which we were trying to create have now been created in a corresponding way. But actually, there's still more inside the data for OS VectorMap Local, because it contains contour lines and text that aren't actually there in this 1 to 10,000 scale image. So there's a convenient bit of space left here in the FME workbench where we can put in a bookmark for dealing with contours. We're going to take just the contour text and simply copy the correct color for that and send it straight out. But we're also going to take the contour lines and separate those into two. There are standard contour lines and so-called index contour lines, which are the round numbers. And we're going to make the index contour lines look a little bit more prominent than the standard ones. And here's the result in MapInfo Professional. You can see a sort of dotted line appearance for the standard ones, and every fifth line, which is at a round number of meters for height, is a solid line, so it's a little bit more prominent. Now, that's accomplished the goal, but if we choose a different style option, instead of 1 to 10,000 raster, we'll try and emulate the Street View, OS Street View raster, which of course is part of OS Open Data these days. That introduces a new kind of feature called road center lines. And so we've squeezed in a final bookmark in the FME workbench, which uses the line polygonizer again to make thick center lines that will be colored according to the style of road, so blue for motorways, red for A roads, etc. And then just copying the line style across into the fill style for those polygons. And here's the result. I think you'll agree, looking very much like OS Street View, but coming straight from our FME workbench by simply going back to the joiner transformer, which we put in the top left-hand corner, and choosing to read the style, one of the 6 styles that creates this impression. Another one of those 6 styles we could choose is the black and white raster. And if you look down in the lower part of the view, but towards the center, just to the north of the portal to the railway tunnel. You can make out the black and white stipple pattern filling the buildings. This is a characteristic of Ordnance Survey's black and white raster product. It uses no colour tinting but has stipple patterns. And the workbench, through its custom transformer, just creates that effect if you choose the black and white style. But none of those are actually my favourite, probably because it was devised specifically for the OS VectorMap local dataset. Ordnance Survey's so-called standard style is the one that appeals to me most. And it comes in 3 versions, designed for rendering at different scales. We'll just have a look at the middle one of those, called Standard 2. And here's the result, with the roads coloured according to their style, and much of the line work made shades of grey rather than the heavier black colour, which I think draws a bit more attention to the vegetation, like the woodland features and that sort of thing. So that's exactly what I meant at the beginning by using Excel as a control panel to drive the FME translation. Just choosing a different tab and doing nothing else, rerunning the translation, we get the completely different appearance. And here's how it looks in FME's own universal viewer. It'll actually look exactly the same in any software because we're not relying on the capabilities of the viewer to render these things. For instance, FME's inspector can't actually deal with dotted or dashed lines, but you see they are clearly in view here. It can't deal with different fonts in the same layer, but that's what we've got here. It can't really deal with scattering symbols through polygons, or even rotating symbols, but that's what we're getting, because we've taken the data and made it universal. That was our goal, to process it once and have it rendered anywhere. And it turns out that if everything's converted into polygons, it's WYSIWYG, as they used to say in the early days of desktop publishing. What you see is what you get. And that means that if you print it out or plot it at any scale, again it will look just the way it did on screen, because we're dealing with polygons that are sized to fit the ground. So the resources we've used in this project include a spreadsheet of Ordnance Survey suggested styles, and that's available for download now from our website www.misoportal.com. There's also an FME workspace I've made called Demo OS VectorMap Local to Map Info, and the custom transformers that it uses. There are 7 of them: the 1 kilometre tiler, area symbolizer, the cross pomy creator, hasher creator, line pecker, line polygonizer, and symbol renderer. These resources concerning FME are not available free of charge, but if you are interested, please just drop us an email or contact your Dotted Eyes account manager and we'll see what we can do. If you go to the MISO portal website and look along the top row, choose the software menu item, and along the second row choose the FME menu item, then scroll down till you reach the part with sample FME files, and I've highlighted in red that Excel spreadsheet containing the Ordnance Survey style guide. So that concludes this session about cartographic rendering tricks for OS VectorMap Local using FME. I hope you found it helpful, and we'll look forward to keeping in touch. Thanks very much. Bye-bye.